Hi, I'm Toru Tanzawa. Thanks for coming. I'm going to have a series tutorial presentation on charge pump circuits. Please send me email to this address if you have any question. If you have any more interest on this topic, please visit this website. You may find another interesting things. So far, I discussed the equivalent circuit model on the output voltage and output current and input current and output voltage and also power efficiency. And in this tutorial, I'm focused on the optimum designs, how you should design the charge pump when you want to minimize the circuit area, or if you want to maximize the power efficiency, or the optimize the charge pump in a balance between the area and power, or the frequency, and so on. This optimization is aiming at maximizing I out, meaning maximizing P out, and the circuit area is given. So here's the V out I out plane, and you can draw several lines. Even the circuit area is provided. You have freedom on the capacitor size per stage and number of stages. So you can select the large C with the small n to large n and small c. And there is some case between the two extreme case. As you already know, the Vmax increases as n increases. Whereas the slope, which is expressed by output impedance, which increases as the n and decreases as c. Therefore, as the number stage increases and the slope should be more gentle, and x-interception increases. And therefore, if you look at the three typical curve lines, and if you get the maximum output current at VPP, so the number 2 line must be selected. And this paper provides the output. When the BPP is provided, then your charge pump must have Vmax is twice as large as BPP, or in other words, the BPP must be half of Vmax. So to meet this equation, this is equivalent to this equation, where the Nmin is defined by this equation. So with the enemy, the charge pump barely generate VPP with zero output current. And this NMIN can be calculated when you are provided Vin and VPP. And then using this equation, your number stage must be meet this equation. This is output current versus number stage n under a constant area. So you would have a concave up curve like this. And at this point, number stage must be given with this equation. So it is a very simple way to select an opt. Then if your target I out is, say, twice of this point, then your charge pump must be increased by a factor of 2 from a given constant circuit area. Then your capacitor C can be determined. So that's it. Then you run a spice simulation to confirm that method is okay. If your concern is primarily on the rise time, and if you minimize the rise time, then you should select the number stage to meet this equation. On previous slide, this factor was 2, but in this optimization, you should select 1.4. Again, if you so small n but large C, the output voltage goes up rapidly, quickly, but saturation is a little lower, like this. And number 3 case, the number 3 case has larger n but smaller c. And so number 3 has the highest, the final voltage. However, the rise is most the slowest curve. And so if you have the target VPP here, and then this number 2 must have the minimum rise time. This fact is based on the dynamic model as I presented in the previous presentation. So steady state Thevenin equivalent circuit model plus equivalent capacitance term, which is given by this term. So you just add the 1/3 of the total capacitance of a charge pump connected in parallel with the load capacitance like this. So regardless of C load, you must select number of stage given by this equation to minimize the rise time. If your concern is minimizing the input power under a given output current, then you should select minimum number stage is like this, and the optimum number stage is this. This is the same as the case to minimize the rise time, but that's just a coincidence because the approach was very different. So it seems a little complicated than before, but all the parameters are given before you design the judgment. You provided VR being BTH alpha t, then you can calculate the enemy and also an opt. Then you can determine the required capacitance C. That's it. Then you just run the spice simulation to confirm this is valid. So if your concern is not only a single term, but two, for example, area and rise time, or area and power, or all of them, what the number stage should be selected? The x-axis shows the number stage normalized by n-mean, and the y-axis shows normalized parameters for rise time, area, and power. There are several curves like this. However, if you select an opt 1.6 to 1.7 here, then you get almost optimum point for all of them. And this is just 10% higher than the very optimum cases. So if you allow the 10% increase than best case, then this is a moderate point to get all the parameters minimized, almost minimized. Okay, in optimization number 1 through number 4, I assume under slow switching limit or in a low clock frequency case. However, if you may want to optimize the clock frequency as well as the number stage and or stage capacitor size, how we should do. This is the approach to proceed. Well, initially, let's optimize the clock frequency and capacitor per diode size ratio. Then maximize I-out under a given area, or equivalently minimizing area under a given I-out. Or minimize area under a given rise time, or equivalently minimizing rise time under a given area. Or minimize the input power under a given I-out. So this is the curve I-out versus frequency. In a slow switching limit, the I-out increases as frequency. However, in reality, there is the optimum frequency to maximize I-out. So let's look at the clock frequency versus capacitor size or diode size like this. So given stage area, here your freedom is how much capacitor should be used, or transistor size should be used. So if your capacitor increases, then your transistor area decreases. On the other hand, you can increase the transistor area with the smaller capacitor area. So if you want to increase the clock frequency, then transistor must be increased with some reduction in capacitor size. However, in this situation, smaller capacitor, whereas larger plastic capacitance increases the plastic element I alpha T. So this large the alpha T may lose your I out due to loss based on the alpha T. So probably there is an optimum point between the two extreme cases. This is a curve, the output current versus clock frequency with different transistor areas. X1 through X4 indicate size increases with this factor. You draw the curve like this. Of course, larger transistor area can have a higher optimum higher clock frequency to maximize output current. However, too much transistor area reduces the peak output current due to the loss based on alpha T. So in this demonstration, X2 has the highest I out in terms of frequency and transistor size. So in this, the optimization number 5, you could determine the switching circuit topology. For example, you have a gate overdrive with a 4-phase clock or bulk potential control to reduce the VTH or CMOS type topology. Then, once the topology is determined, then your alpha T should be determined. Then you can run the various simulations with the different capacitor and switch size ratios per given area, and also you can sweep the clock frequency to find the highest output current and the optimum clock frequency, and at the same time you get the optimum switch and capacitor ratio. Then you should calculate the optimum N with this, and finally you calculate C to meet your specification for higher output current, rise time, or input power. This is the optimization number 6, which is the last optimization method, comprehensive way. So here, this table shows the demonstration parameters, and as shown in the previous slides, the CT from a transistor and capacitor C composed of each stage. Then we are looking at some clock frequency range with the different transistor size. and different number stage. Here's the R. This R indicates the transistor channel resistance and output current with the different clock frequency. In this simulation, N is set at 10, and also you get the eta versus R like this. So this is not good way to find the optimum point. So you just change the plot. For x-axis, the you just plot eta versus I out based on those two graphs. For example, this point has this I out, say 60 microampere at 2 kilo ohm with 12.5 megahertz. This point design has 30% power efficiency like this. So this point is plotted into eta versus I out. In that case, probably here. There is so another method is the parameters are the resistance vary rather than clock frequency. So with the same data points, but you just use clock frequency and you sweep R, then you can find the optimum point where the eta and I out both are maximized. So for example, in this plot, this frequency can get the eta over 30%, whereas I out at say 70 microamp. Whereas with 50 megahertz, you get 200 microamp with 25% eta, for example. So similarly, you get that data. So eta versus I out trade-off conditions. Then, so previous slide shows the eta versus I out. However, I out itself should be the specification of a circuit. Therefore, to get the target I out, you have to estimate the area. Then the eta versus I out plot can be converted into eta versus area, like this. So this is almost a last graph. The parameters number stages. So there is a trade-off, area versus eta. For example, if your priority is the area, then you should select these points here, which has 20% power efficiency. Or if you have some amount of area room, and suppose 2, then your eta can be improved by, say, about 10%. So things like that, once you get to this kind of graph, then you select the best, the parameter combination. These two are identical conditions, but the spice or the model. So there are some the discrepancy between the two, but the tendency is very close. And error nominally 20% and extreme case is 40%. But I guess you don't have to vary the various simulations in SPICE. You just run the model, the calculation based on this model. Then you identify some good region. Then you should concentrate on that portion using SPICE to get very high accuracy. This is our example, smallest area case or moderate the design parameters here. So the design are pretty different. The number stage different by 40%, it different by a factor 4, and R different by a factor 3. So using the following few slides, I show some optimization methodology for some summary. So you are provided the target specification, input voltage, output voltage, and output current at output voltage. And also your technology is also given. And you can probably select the switching circuit topology. Then the basic parameter here to proceed the methodology. And initially, you assume a total capacitor size, which is not, which doesn't affect the final result. You just start with the assumed total capacitance. Then you should treat as variables EF frequency, C over switch, and number stage N. Then using these equations, you should get those values as a function of them. Then you should draw a graph showing the eta versus I out by varying the frequency and C over SW switch. And you identify the optimum point where the both eta and I out are maximum. Then instead of I out, you should calculate how much area that design requires per F and per N. Then you scale up that capacitor size, or total capacitor size indicates the total charge pump circuit. Then now you get the total capacitor size, I mean the total area, as a function of the frequency and number stage N. You also have the ether as a function of frequency and n. Then finally, you should plot the ether versus area, and your goal is in the left top portion, and you select some of them and check the simulation to see if your design is okay. That's it. Thank you.